Okay, so I continue talk about quantum trajectories, and today we focus on the quasi-compactness of quantum trajectories. And we just remind what was the theorem we wanted to use. So the theorem of the minus proof theorized by indirect. Okay, we want, let's choose the operator space B. So, B. Given that we wanted these three assumptions. So first, that if we're looking at Q of all the function in order space of not smaller than one, I want this relatively compact B handled with the seminar. Here's my test assumption. I want the existence of M where F smaller than F for all my function in my Banach space. And I obtain the digital search inequality. Mean that there exists four quadrats and F is smaller than some of F plus F on F or polar than the spectral radius of Q. And if we have these three assumptions, we have the quasi-compactness of the operator Q on my Banach space P. So here, my goal is to prove that my operator pi on the alpha holder, on the space of alpha holder continuous function, handled with the alpha norm, is indeed verifying the assumption. For the quasi-compactness of pi, okay. So to prove this, everything will be included in what we prove to prove the invariant volume. Remind that we proved yesterday every space of alpha holder continuous function it was smaller than some constant at for alpha plus another constant multiplied by the supernorm norm of F. So here this supremum norm is playing the role of the semi-norm in the norm. So in the I will call it ITM. Right. So ITM for its analysis. So we have this. So now we are almost close. The only fact we need is, okay, we need to know what is the spectral radius of the operator pi, and also we want to know if I can find some op here, because for the moment here we have only Gn. Okay, so we need to prove that O pi equal to 1 plus there exists some n or 1 such that for n large enough, C pi is smaller than R the power s. That's what we want. But we are lucky because we know something about G of n. It's the last thing we proved yesterday on this function. So yesterday what we proved that there exists a C. I've already a C for the case. And lambda 0, 1, such that for every n integer, your n is smaller than k lambda the power n. So since we have this, if I'm taking n to the power alpha, the same the lambda to the power alpha will be also smaller than 1. And so for n large enough, I will get this op.
I have a question. I have a question.
Yes.
Is the norm in the term PNF the alpha norm?
Here, yes, it's the alpha norm, yes.
It does not correspond to the statement 3 of your left-hand board.
Yes, here it's actually the Banach space. So here it's more general. It's here. It
Right.
will be the alpha norm.
Right, but you said that the alpha norm plays the role of semi-norm.
Oh, no. Here it's infinity. Sorry, I maybe wrote it badly, but here.
Yeah. Okay.
It's a supremum who's playing the role of the semi-norm. Sorry. Yeah. Maybe I wrote it too smallly and was not able to see on the screen. Sorry.
Thank you.
Okay. Yes, maybe I should write. I should write the. Okay. So now we have this. So that means that for n large enough, we have exactly what we wanted, but here f for alpha will be smaller than some r on r to the power n. We can fix as the alpha norm of f plus some r. So here we have almost the Dominant inequality. We just want to prove that R is indeed smaller than the spectral addition Q. What we know, we have R between 0 and 1. But also what we know if since phi is Markov, have a P of 1 equal to 1. And so that implies that 4 of phi will be greater than 1. So here we have directly we have directly proved the Dublin quartet inequality. Source, one source, the Dublin quartet inequality. So for item 2, so we can directly by Markov property by F infinity is smaller than F infinity. Okay, we have it directly. So as usual, this system is not so hard to compute or to verify. Sorry. And then we have the item 1. So everything is also hidden in hidden in this inequality. So why? Because if I'm looking at this thing, I want to prove that the image by phi or by f in C alpha does that f alpha is smaller than 1. Relatively compact in C with the infinity term. And here we have an equality for every n. So that means that if I put n here, here will be, we have some G1. And since f alpha is smaller than 1, of course, infinity is smaller than 1 because it's greater than f alpha. And here we have for n equal to 1, some constant k independent of f. And so we get the equicontinuity of this set, set. So relatively compact in alpha kind of norm. Yeah. By the important. Five of inbounded. We are applying Arnaud's code theorem. Theorem, we obtain the relative capacity. And finally, we have the positive compactness of pi on that. So yes, all the work has been done before with all this technical lemma we provide today. And at the end, we use this Ionescu-Tucia-Marinescu theorem. And by just putting everything we proved before, we managed to satisfy all the assumptions. And what directly is the quasi-compactness of this operator. So now that we have a quasi-compact operator, we can now use every property of this quasi-compact operator, and especially this operator pi is of diagonal type. So that means that we have a great decomposition of the operator pi. So here, since four is equal to 1, so all the theoretical eigenvalue of pi are of modulus 1. So if I just take here, here we have 1, we have some eigenvalue. I put it randomly for the moment. And now we have the spectral gap, and everything else is inside. But the good question will be, okay.
Right here, I give this out of one inside a small disk, right? Why there cannot be eigenvalues in the small disk?
Because I'm quasi-compact. So now I have a spectral gap between my peripheral eigenvalues, which are radius 1, and then since you will have like the decomposition with pi plus with what some
What's it in all the what eigenvalues?
the peripheral. So the greatest eigenvalue of my operator pi.
Okay.
And the other one will be smaller, of course. So the question is,
just one question. Your rho is in the space L infinity rather than in C alpha, right? Because before in this proof it was in C alpha.
Yes. The rho is the rho is according to alpha.
To C alpha.
Yes.
Is it obvious that it could be equal to 1? It is improved that it's more small than 1.
Yes. You can also adjust. I can prove it if you want. But by this equation.
Okay. You can write it.
Yes. Just with this equation, you have some constant k and
right.
But if you want, I can prove it, which is to get for everyone or? Okay. So now my goal is to understand, can I give like a structure of this eigenvalue? And the answer is yes, actually. So some propositions. All the eigenvalues of spikes of emerald or some m anything. So that means that the spectrum of E intersected with all the complex number equal to 1 is exponential of 2I by L divided by M for all the M. So it is indeed not like this, but we have a structure of group for mathematical values. So what does it mean? So that means that our operator pi has a very great decomposition. There is and star from 2L for L from 1 to times 1 and for one map bounded such that I is equal to the sum for L going to 0 to M minus 1 of all my eigenvalues. We have a projection onto the associated eigenvector of all my eigenvalues. We have plus something which is negligible. And as before, we have that pk PL is equal to the derive of KL pk. And we have that if we look at K on pk is equal to 0 for every K between 0 and minus 1, sorry. And we have as the spectral radius for the alpha norm of M is slightly smaller than this. So we managed to write our operator pi as this quantity. So now it's more easier to study our Markov chain because now we are not looking at this n, which will be negligible, and we just focus on what happens for my projection here.
Do you claim here that these PL are rank 1 operators or not yet? Rank 1 projections?
Yes.
Okay, so in particular, say that all the eigenvalues, there are no...
we are all simple. Yes. We are all simple. Actually, we have the concept we have here, M dominated eigenvalues for the operator pi, which is M simple eigenvalues, all have the same modulus, which is equal to 1. And here, if you look at, of course, you have 1, and the 1, the associated vector is associated to the invariant measure of pi. No questions? So let's talk a bit about this M. Yes, first time. So here we have this decomposition. So I will go back to the definition of irreducibility we had before.
Yes. Now you are proving the previous proposition or what you are proving now?
No. This we have directly by quasi-compactness. I will talk about the convergence towards the invariant measure now. And where is this M, and how to give a definition of this M.
Okay, but then I don't understand one thing. So quasi-compactness implies that you have this
Yes.
eigenvalues from the circle,
Yes.
plus the previous proposition said that there are nth roots of the unity.
Yes.
But still, I don't see why this projection should be one-dimensional. I mean, it is the VAR cannot be generalized eigenvectors. In the sense, the VAR cannot be vector, which is not an eigenvector, but so I mean, not pi f is equal to lambda f, but pi minus lambda squared f is equal to 0. Well, okay, so maybe we should discuss it later. Okay.
Yes, maybe
Well, why there cannot be Jordan blocks? That I don't understand.
Yes, because of the fact here we have another assumption of pi, which is that pi is of diagonal type. I don't know if you
so you assume that pi of diagonal
but we proved that pi is of diagonal type, so we have the S as a domain type. So yes, maybe pi is of diagonal type. But so if I wanted to prove that pi is of diagonal type, actually I just wanted that the supplement of n 1 or alpha n. But since we have that the spectral radius of pi is equal to 1, actually we can prove that our pi is of diagonal type, and then we have, of course, S domain eigenvalue, and we can't have the Jordan block. And actually, the proof, so I didn't do the proof of the diagonal type, the proof of the fact that we have these assumptions equivalent to the fact that we have the diagonal type of quasi-compact operator is based on the decomposition with Jordan blocks of the geometry.
So I see the equivalence, but okay, so
yes.
So we didn't prove this, right?
No. Yes, yes, I forgot to. No, it's
understand that.
Yes, I forgot to say because it was indeed important. Okay. So now let's go back to the definition, the assumption, and in particular the definition of elusivity. Because I remember last time I said elusivity for some theorem, but it was a strong elusivity which was assumed. So what we say is the following. We say that for L an integer and the unknown, which is a submu invariant the base the slits and we have this invariant to space. So we say that this family of subspace is L cycle so here for mu almost every V, we have a VI is included to the L plus 1. And if I have some L, the L we go back to 1. So, yeah, so here for every I in L with plus 1. So that means that, okay, we have some decomposition, and take it with 3. And I go from 1 to 2 to 3, and if we to so here, of course, there exists some L cycle because I can just take L equal to 1, and that works. But with reducibility, the L could be larger, so the larger L such that there exists such a decomposition. So it's called the period of phi. So here phi is the quantum channel associated to the Markov chain, and we denote it by it. And actually, this M is the M we find here. So here, if we have a strong irreducibility assumption, we cannot have this kind of decomposition. So I mean that the largest L would be equal to 1. And so that means that here we have only one eigenvalue of modulus 1. And here we have just, okay, a collection towards the invariant measure plus something else. But here, since we have only a disability, we can have more bigger decomposition of my invariant subspace, and then here we have some period which can be greater than 1. Okay.
I are subspaces in C alpha, right?
Yes. There are subspaces of C. There are subspaces of CD. The DI on CD. It's linked to the reducibility assumption of
Okay.
they are all living here. And of course, here, if I have an invariant subspace, but of course we have an invariant subspace, we'll have that this, it will be not about decomposition of CD, because we assume that the reducibility assumption, the only invariant subspace is equal to CD. You can generalize for a minimal invariant subspace E, but here we are seeing in CD. Okay. So now I want to prove the convergence towards the environment by using the decomposition. So we define the Wasserstein metric. So So for mu, and so 2 quality measure over with the right measure, we have that the reception metric of sigma tau will be the supremum for F. So a Lipschitz continuous function of PCD, such that we want that the norm of f infinity equal to 1, and we take the difference of expectation, so f minus f mu. So we are looking at every like this, and here I define my Wasserstein parameter. So is Wasserstein parameter. So here's the one because we are looking at the we can define it for other value. And so here the theorem we have is the following. But okay. The Wasserstein metric of 1 over divided by m of the sum of mu will pay m plus l against the invariant measure is smaller than some c lambda to the power n. And here it's so it's true for any nu. So there exists some c and a lambda in 0, 1, such that for any quality measure mu, measure mu over PTD have this convergence, which is geometric. So let's just remark that if we have the strongest gravity, m will be equal to 1, so it just will be only nu pi at the power n, which is classical convergence for the Markov chain with finite space. But here, since we have the period, we have to do a sum over m. And here we have only this part, which converges to this part. And my goal is to show you by this decomposition we had before for the quasi-compact operator, how to get this inequality. Actually, here it's again the result of Tristan Benoit, Martin Kratz, and Potra and Clément Pellegrini. They use a different technique because they didn't have the quasi-compactness of the pattern pi, so they had to do it more carefully. But with the quasi-compactness, we will see that it is almost immediate to get this kind of theorem, and it not requires a lot of work when you have the quasi-compactness. So let's do it. So to do it, we need first a small lemma. And the lemma. And the lemma is the following. So, for every f now we have this equality. 1 over m of square is equal to the invariant measure of f plus over m of f from 0 to m minus 1 on the rest. So here we see this just as some function. Okay. So it's not too complicated to prove it. So let's have the under this function. We derive by Zm I just not about it every time. And so by the previous decomposition, but if I'm looking at 1 over m of f from 0 to m minus 1 of this quantity, I know that I'm able to compute the power of my pi. So that means that here it's equal to this. Here we have another sum, which is another sum from j going to 0 to minus 1. And here I have my Zn m at the power L nm plus j. Some projection p of j. S plus some n. We have this power of f is equal to this. Because here we are just looking at this kind of joke. Maybe just change here. So we have this decomposition. But now, since the z of m are roots of the unity, that means that a lot of these terms will vanish because the sum will be equal to 0. Here we can separate into two parts. So here, if you look at it, we have m unity. So here, this part will be equal to 1, so we just have this as a power j. Okay, just equal 1 over m to L from 0 m minus 1, negative 0 m minus 1. we draw them as a aj. Plus we just have this because here this part is equal to 1 because we are at the root of the unity. And so now we have that for every. So we can exchange the sum. Yeah, chuk. Yes, I can see every stuff. Yeah, we have another sum, which is just 1 over L, or something which will be negligible later. So actually here, for j different to 0, everything here is equal to 0. So for j different to 0, the sum from L going to 0 minus 1 of expression j as the power L is equal to 0, and for j equal to 0, sum is equal to L. So at the end, what we find is that this quantity here, 1 over m from the sum from L to m minus 1 in L. So since everything vanishes outside of j equals 0, we have m by 2 square. So here we have just the projection T0 for f plus something else. Only thing we need is, okay, is this thing the invariant measure? So the answer is yes. Why? Because if you apply the invariant measure here, by the fact that pi is invariant, here it will be only equal to the measure. Here we call it SAR. Here. Applying invariant SAR. So we get the left part which is just equal to the invariant of f. And here we have mu of invariant of f plus 1 over L here we can just mu m and then plus F. Okay. And here, so this is a constant. And here, since we have like rho of m is smaller than 1, limits when n goes to the infinity of m plus L. Okay. Equal to 0. And s to infinity. So here everything vanishes. and by infinity have a new invariant of f is equal to 0. It is fine for everyone. Ahmed.
I think you just implicitly leave that the P0 is the projection to vector
Yes, yes.
1, right?
Yes, yes, yes.
That implies that you win, but
Yes, yes. Okay. So now this decomposition, so we have almost finished to get the convergence toward the invariant. So the proof is not too long. Convergence. So let's have indeed norm of f is equal to 1. So I want to estimate here. Oh, what we want to estimate. Now I can just use what this expression before, so it is equal to E that over over to estimate this. So here, according to what we had before, it just the value measure f plus the rest is to some. So here, this minus this is equal to 0. So I just have a new of 1 over m of this. And so now I can apply the triangular inequality, and it is smaller than 1 over m of L from 0 going to m minus 1 to here, new plus L of f. And my goal is only to know how to to know how to assume this, but now we just have to use the fact that the spectral radius of M is smaller than 1. So let's just go on the report. So here I have 1. Here I have both alpha of M. And since I have a gap, I can find the rho between rho alpha of M and 1, such that right for every n. No, that can see also. And here, n as the power n will be smaller than c rho as the power n. Here it's not the rho alpha of n, it will be some rho between the two. Because of course it will be false with this rho because rho alpha is the infimum of the n power n. So here you take some epsilon, and because you know that it converges to rho for some epsilon great enough, you have it. So because we have this, now it's almost finished because this smaller than means it is smaller than 1, so we are smaller than n plus cell. We are smaller than c rho and the power n plus cell. And now just have a sum. So at the end, we can say this we call it here lambda n. So at the end, lambda n is smaller than 1, but just 1 over m multiplied by some constant c and going to rho m, so of rho m plus l plus l. So here it doesn't depend on L. So here we have 1 over m and c rho m. And this only depends on m. So we put it in the constant. Rho of m could be our lambda, because rho of m will be also smaller than 1. And then we get the existence of the lambda. And so there is indeed another proof, but it's way more complicated when you don't have this decomposition, and it is based on estimation of some processes, and it's way more longer to get the convergence. But what we can realize here is just we almost did for free because we have the quasi-compactness of the pattern, and of course the diagonal type property to get the good decomposition.
Some questions.
Yes.
You could have taken alpha equal to 1, right? So you don't think alpha smaller than.
Yes, but alpha.
I mean, it works on
yes.
1 is bigger than alpha.
Yes. And of course, here it's the spectral number for alpha equal to 1. So it's just two use of writing alpha. But for this case, we don't need alpha, we just need Higgs.
Yeah, am I right that in fact you defined this distance not for Lipschitz function, but also for all our continuous functions? and everything will be the same, or there are some subtleties. I think you define your Wasserstein distance
Yes.
as the dual of Lipschitz function, right?
Yes.
So you would say that I take into account for functions which are only alpha.
Here it will work.
It would work.
Yes, here because yes, here it will work completely the same because you saw that at any moment we need.
Yeah, so
Okay. Okay. So now we prove the convergence, but now we want to tackle the limit theorems. But to tackle the limit theorems, as you remember before, when we studied the Markov chain on finite space, we needed good perturbation. So here we take some time to present you the perturbation. And I think it's interesting to see how to prove that they are indeed analytic, because we have some nice results about the analyticity of this perturbation. So let's go. We will try to move limit theorems for two different processes. The first one is the empirical sum, so the classical. So here we will one from H. A function of C alpha, and the goal is to give a CLT of the process dependent H. It will be all the sum and of my f of s t. So the classical one. So here, to study this, sorry, H. To study this process, we define for Z in C the operator pi of Z, which will be a perturbation of pi, so still acting on the space of alpha over term, so acting on its alpha. Okay. And how do we define it? It's for every f it's alpha and x part. The element of the complex projective space, the level of f of x will be equal we will just add some exponential z of h. So what we can remark here, if you compare it to pi, it is actually equal to pi of the exponential of zh f applied to f. Okay, so here it's one perturbation we will study, and the second one is linked to the random product of matrices. And it's the Lyapunov exponent. So here, when you are studying the Markov chain, I remember you are looking at the Markov chain at n plus 1, which is equal at Wn.xn, where Wn is my random product of matrices. And so an interesting quantity to study in the domain of random product of matrices is the following: is ln, which is equal to the log of the builder. And what we call the Lyapunov exponent. So it has been studied by a lot of people. So the precursor of Doctoral and Lacroix, they have a very good book about the study of the random product of matrices, and in particular, they studied this process. However, we cannot apply their techniques because in their techniques, they assume that the VI are invertible, and of course that the law of the VI are IID. Here it's completely not the case because the Vn depends of the previous step of my Markov chain. So everything they did, we cannot apply. And so we had to find new ways to study such a process, and the quasi-compactness of the operator will help us to do it. So here it will be almost similar at this perturbation. So here we're looking at this. Okay, we have some h of x. So how we can find the...
I have a question.
Yes.
There is no limit for the Lyapunov exponent. There is no 1 over n, limit of 1 over n to get the Lyapunov exponent. This thing here depends on n.
In the definition of ln,
Yes, sorry.
And there is also limit, right? Or is also there is also limit. Or
no, here the limit it's for later. Sorry. I forgot it. But yes, it's just to study it, but I didn't tell it. So here, how will we study it? We have a perturbation I will call gamma z, which is another perturbation of pi, which will be given by gamma z of f will be equal to almost the same thing. We want exponential of z of some log of px, and the same with the rest will be the same. However, here, if you compare to what we have here we have h, an alpha Hautecoeur function, so everything will be fine. We will be able to do the condition quite easily. We'll see a bit later. However, if you compare here, the logarithm is very is not alpha Hautecoeur, because here v of x could be equal to 0 and could approach 0 very fast. So actually, in the proof of Boulevard and Lacroix, they had a similar perturbation, but since they had invertible matrices, the value of x was not an issue because never value of x would goes to 0, and so they had like good way to study this kind of operator. But for us, it will be way more difficult to study this. So I will give you how my goal now is first to show you the history of this with some techniques, and then I will go back to gamma z, and it will be something more, I would say, algebraical and some functionalities, big theorem. But first, let's go to this and show how this perturbation is analytic.
Your Z is small or Z is arbitrary here?
I would say where Z is living. For the moment, I didn't say.
So what is that?
It's one of my. I didn't say for the moment where Z was living.
Okay.
But when I will give the theorem, I will give you because the Z here won't be the same Z here, and the analyticity will not be in the same space. So let's go. It's exactly what we have. So the perturbation then you file Z is analytic. So you can choose any Z. Okay. We won't have any issues for this. So how do we prove this? Actually, we will do it. We want to show that something is analytic. So I think I just want to give a series expansion of pi of z. So the goal is to write pi of z as a sum for n goes close or close. So z as a power n divided by n factorial for some pi of n, where pi of n is a linear Markov. So here, my pi of n will act again on the space, and for every f delta and x infinity, my pi of n will do exactly what we expect. It will be equal to h of n in x I just want to get the expression of zh. So I do it like this to get okay. So to prove that it's convergent series,
But H is bounded, right?
Yes, but you are living in H is in the projective space, so you are a continuous function of a compact, so you are bounded.
Okay, so that why is not obvious that this converts or
No, don't worry, it won't be too hard.
no, why is it trivial? I mean, I really don't understand. You're in C alpha, you need to prove boundedness in C alpha.
Yes.
Okay, sorry.
Yes, it's just the alpha, which is a bit more complicated. If I was in infinity, it would be exactly directly the case. But what I want to prove is that the sum of alpha norm of n is finite. So it is a convergence series for every z. The way we have to give a good, but it's not an issue because we almost did all the works before. So, because if you look at the left F, the space of continuous alpha Euler function, and X, no, just F, not this. So we have a Pn of F is actually equal of pi of h to the power n f. Since they are both sheets, we still have both order, we still have an Euler function here. And actually, we proved before so that we have P, H, and F. It was smaller than some constant Hn F alpha plus another constant Hn F infinity. Because we proved it before, so I just use this applying to Hn F. And so now, yes, we have this. So here we have the fact that here it will be smaller than Hn alpha F alpha plus C2 Hn infinity F infinity. We have this, and at the end, here we have this, which is smaller than this, and we have only a constant which only depends on the alpha Euler norm of H and the infinity norm of H. So here it's smaller than some constant. Here, multiplied by F alpha. And that means that we are smaller than something like that. But we know that since we have z to the power n, it will be z to the power n H alpha, and we are smaller than something which converges. So here, everything has been done before. We just have to apply this. And spot it properly. So that smaller as some constant. À chaque fois. Right, convergence of the series. And equal the sum.
Yes, usually. You seem to use here this Darwin Forte inequality, right?
Yes, I use
But is it really necessary? Because you could have said that this pi is bounded in C alpha, because after all, your second term you estimated by the first one.
Yes. But that's how I prove it actually. I just wanted to prove it that indeed it was bounded in C alpha.
Okay.
That's right. That's all I wanted to prove. But to prove it was bounded on C alpha, I use the Dublin Forte inequality.
Okay.
You understood everything completely. The only thing I didn't do in the following step is I didn't prove that phi of z was indeed an homomorphism of C alpha. That means that I'm going to C alpha to C alpha. Is an homomorphism of C alpha. But it also based on the Dublin Forte inequality. So let's prove it. Like that. Pareil. Z of alpha is equal to P of exponential ZH of S alpha. And again, we can use the Dublin Forte inequality. So we are smaller than from C F alpha plus C2 and again, we can bound as before here by some constant. So we have F alpha plus 2 exponential. So we take the modulus of the real part. Here we have some h infinity. Here we have n infinity. So we are smaller than some constant only depending on z and h. F alpha. And we are indeed again a bounded linear operator from C alpha to C alpha. And we see really again what this Dublin Forte inequality is very strong. Okay? Okay. So now I prove the ICT of the first perturbation. Now, let's try for the second one. But the second one, we will see that it is way more harder to do it. So for the second one, we need more assumption. We take some. So will be between 0 and 2. And lambda should be between just something positive, and we want that for every space in 2 minus 2 plus delta, the moment of order 2 plus s will be finite. So we add something a bit greater for this, only based because since we have a logarithm, it has a lot of issues, so it implies that we need more moment assumption for my version.
So that there is delta such that
Yeah.
why not write
Yes. So yes. What did you mean?
No, if there is delta, why can't you write v through 2 plus delta is integrable? Or because there exists delta, right? Or you may need the delta. Right?
I want some delta substitutability. I need, but I can go further from 2 because for the moment the only assumption I have is this.
Yeah, but if you assume that v 2 plus delta is integrable,
yes,
then for any s smaller than delta, smaller than 2 plus delta, it will be still
yes,
right?
Yes. But then yes, I just need it on some interval. So I need this, and so if I have this, then I can define the bond. So for every, so let's we call it U. It will be all my Z in C such that the real part of Z is in 2 minus 4, 2 plus delta. And the map Z to gamma Z is analytic on U. So we just have like, if I do a drawing, and 2 here, we have minus 2 here, 2 plus delta here. Defining the complexes and the complex space, we have all this band, and on this band we are like. So we don't have the C, and it's only because of the logarithm. We can't have it on the whole complex space. Yes.
Statement. And if this is integrable for s, let's take s equal to 2.
Yes.
You say that you cannot go to 0, so it won't be allowed for a real part of z between 0 and 2. You really need.
Also in yes.
No, I think it is okay. The question is, you cannot go to zero because it's singular that your singularity is.
It's here because we have the z should be between here because you will have the x2 plus z. Like if you remind, like gamma of z is this actually. If I write it like this, with the log like this, so it's like this. So I need my z between -2 and plus delta. So
Yeah, so this is exactly my question. So I understand that you cannot go.
I can go to zero.
Yeah, this is.
I can go to zero.
Okay.
Because I will have the fact that if I go further than zero, my b outside
zero. The question is
yes, but even to zero I can't. Because I will have some issues with the norm of v of x. But
you cannot go to -2 in that sense. You cannot.
Yes, I can go to -2.
You can go to -2.
I can't.
You cannot go to -2.
I can't. But everything, like, I don't have a lot of good explanations to how I can't go there. The fact is, when I do all the computations, at one moment, I need that my power has to be greater than zero. It's like, maybe with some other techniques, I could say, okay, we can go to zero. But with the techniques I used, I can't go to zero. So yes, it's a bit weird, but like it's hidden in the computations. So I would just say, okay, if I want to prove such an ICT, we could say, okay, we can use the same method. So how would it work? Between the first method, I would do the same. I would say, okay, we take some gamma z, and I would like to go for n to infinity, put some z as a power n divided by n of some gamma n. So if I want to do this, that means that my gamma n of f has to be this. Okay. So now, the real issues is what we did before is here we have H, which was alpha law continuous, and we will be able to only use the property of pi. The issue is now, if I want to give an estimation of gamma m f alpha, so first I need to prove that gamma n f is still something alpha Euler continuous, and then I have to give an estimation of this. So I won't do it. I won't do it because I will show you another proof. But actually, it is possible to do this. It requires a lot of computations. So I did it. It took like 5 or 6 pages to do what we did just before in one line. And just because of the log, I had all this trouble, and it was completely. It was possible, but it was very hard. So I will not show it because it just will be some long computation, but you have to do the fact that keep the Vx square with a log to have something which is, in a sense, alpha order continuous and go continue. But we can go way more faster with some very interesting theorem. So I think it's a very nice theorem, which is, I don't know if it's well known, because actually I learned about this theorem, and when I was reading a lot of papers about this kind of stuff on the archive, nobody was using this theorem. Actually, it's one of the reviewer of the article who told us, oh, there is a theorem, and which is a very old theorem. So I don't know why it's not so popular, because it saves us a lot of computations. So it works, but it's fun. What is this new method? So the method 2 is based on the theorem of Arnaud and Hautecoeur. From almost 30 years ago, but maybe since it was not so well spread, people don't know it. And it says the following thing. So we take some file going to X, a locally bounding function. And we want that Q is not present. Let's see. And we want that X is a complete spanner space. So here, if you look at what we want, if I compare, CU will be our bound, and X will be the space of linear bounded space. So now, take some S prime. So I will explain what it is, of course. Be a separating set of X prime, so the dual of X. So that means that if I take some X different to 0, so here my X will be some linear maps. So there will exist X primes in the dual such that X prime of X will be different to 0. So we just want something like this. So I will show how to get this with our operator, because it would look like a bit could like a bit abstract. And what we have is, if I'm just looking at the anicity of x prime of phi going to C. So here I just have forgot the word in English. But
It is all working for all functions, the rate is all working.
Yes. But I wanted to say, yes, I forgot the word in English and French. So if it's holomorphic, then for argument's sake, let's try S prime, then C is an additive value. So our goal is to prove such a theorem, and the fact is actually here, what is good is that we transform this to just a question of anicity for only this function. So it's way more easier to prove that this is analytic than this is analytic.
So in the case of Hilbert's plate, this is definitely very known result. It says that if it is all the functions are working, then
yes.
But you said that in the Banach case, it's more difficult to prove it.
Actually,
these aren't
the issues is okay. If I wanted to say the fact is analytic, because there is a well-known result of Cato which say, okay, I just want to get it on the dual space. The issues is here we are working on the C alpha, and there is no good way to characterize the dual of the alpha Hölder continuous function. But actually, what says this theorem is, okay, we don't need it for all the S prime. We just need it for some S prime instead, which is very nice. So it simplifies a lot of computations. And indeed, for our case, it will simplify everything. Because now, all the computation we did here for gamma n, well, of course, it is an overproof, but it's a bit more complicated. So here are settings. U is equal to our bound, so our zeros. So X is it's a 5. It's a function z to the left. Okay, so first, the local goodness. So here we will specify our alpha, because we just need for some alpha. We set alpha will be equal to 1 minus 2 over 2. So here it will be alpha. It seems strange, but well, again, it's only based on the computation, and we have to find this alpha. I can't say more about this, the reason of this alpha. I just the computation told us, okay, we have to choose this alpha. And for this alpha, gamma z is indeed going from the alpha adder function to the alpha tandem function, and we have some estimation from the norm of alpha. It is given by this. So again, because of the logarithm, proving this is very long, so I won't do it. It will be just long computations. And what we remark here is why we needed the integrability, because here, when you do it, you arrive at the fact where you have this and this. And look at it, if you take -2 here, you get 0. And if you get 0, if mu is not a probability measure, you get something infinite.
Your mu is not a probability measure.
No, mu is not a probability measure. And it's a priori not finite. So here, if you take...
Okay, then what I was saying is wrong, in the sense that if it is integrable for 2 plus delta, if it is integrable for 2 plus delta, then it's integrable for 2.
Okay, I didn't understand. Okay. So mu is a measure on
but is it finite or not necessarily?
Mu is not necessarily finite.
Okay.
It's just a measure on MD. So that's why here, if you take -2, you get 1, and a priori it's not something finite. But if you take a finite measure, you can do it, of course. So yes, I won't prove this again. It's long computation, but we are able to prove it, and it applies the local goodness of my operator German. Okay. So now let's prove the list. So we want to apply the Arnaud-Vygotsky theorem. We want to apply the Arnaud-Vygotsky theorem. And for this, well, we already defined u and x. What we miss is our s prime. So the s prime will be the set of functional x, the x prime, such that, so define f of x outside is equal just outside vector. And this for every f. Ici, alpha, and some factors implicitly. It's okay? So now, you can find such a psi in the space of the linear map, the linear represents alpha. And we want to show that it isn't separating. So we can assume, that for every alpha f is arbitrary, we have a psi of f is equal to 0. And what we want to prove is that pi is equal to 0. So that will show the separating part of S prime. So let's just prove that psi is equal to 0. Okay. So it's not like this, it's more. Yeah. I want 13. So I want first to prove that we have for every f we have this. So that implies I'd say of f is equal to 0, and then it implies that psi is equal to 0. But if you get this for every f in C alpha, of course, if you apply for a good choice of f, you get that psi of f is equal to 0.
Take f equal to 1. Can you take f equal to 1?
You can take f equal to 1.
But then psi will be 0.
Yes, then psi will be equal to 0. Because it's true for every x and for every x in PCD and f in C alpha. So you want to assume that if this equality is true for every f and x, that implies that psi is equal to 0. So that will mean that if you take, if you go back to the definition of separating, that is, if you take some x, so here, or x is here, so if you take some psi here, there will exist some pi f of x of psi, which should be different to 0, which is the case because if you take something different to 0, of course, it can be equal to 0 for every f and x, for every f and x in C alpha and x equal to PCD. Because if it's the case, that would mean that psi is equal to 0.
Okay, so
Yes. It's what you said. It's just to prove that S prime is indeed a separating set. But S prime. And so now we have U, we have X, we have S prime, and so now we just need to finish verify the assumption. So let's go. So we want to look at F R X CD. And we want to look, so we wanted to prove that X prime of phi was analytic for every X prime and S prime. So here, actually, if you just take X prime in S prime, you have this, okay? So X prime here is equal to phi of X. Yes, so the same X, but in our settings. And so if you're looking at of gamma z, it is equal to gamma z of f of x, which is equal with this. And here I just want the ICT. I just want that Z. So we need just to prove that Z gives on the bond. But here we have it directly, because here this function of Z is analytic. So by the fact that we have an integral, we're just choosing the holomorphy under the integral, and we get the holomorphy of the integral. So Z two plus Z F dx is analytic on the bond. So by holomorphy under the integral, yes, but Z who are integral analytic. And here is true for every X and F. So now, by applying the theorem, we get the identity of capacity. So, R equals T give the identity of capacity on the bond. Well, I find this, of course, this proof is a bit more abstract, but I find it very nice because we had this issue that the characterization of the dual of C alpha, and it shows us that, okay, we don't need it to characterize it. We just need a spanning set of C alpha. And here we have a good way to find this spanning set just with phi of fx, which are very natural actually. If you see this, it's just, okay, I take an operator and I'll apply what I want. So here we prove the ICT. So I don't think I have time to start the limit theorems, but tomorrow we will talk about the limit theorems and also what can we do further, and the goal is to give a nice conclusion about this course and the quantum trajectories. So I will stop for today, and I hope it was not too abstract today, because there was a lot of functionalities and stuff like that.
Thank you. Very well explained. I fully understand. Very hard. Thank you. Any questions?
So do you have any question, Dimitri?
No, it's okay. Thank you very much for your talk.
Okay, thank you.
Very simple. Tomorrow, I will be online.
Okay.
Thank you.
There are no questions, and that's it for today.